Hi everyone, today let's talk about first order ODEs. And more specifically, we're going to talk about, in 2.1, we're going to talk about linear ODEs. So let's start by saying, consider the first order linear ODE y prime plus p of t times y equals g of t. We're going to call this equation 1. So let's consider this first order linear ODE. How do we find its solution? Well, there was this very smart guy called Leibniz that he discovered a specific function that if you multiply your differential equation, you're going to be able to solve it. So he found out that this function, that we'll call it mu of t, if you multiply by this differential equation, we're gonna see that using product rule, the things we learned in Calc 1, we're going to be able to solve this differential equation. And the mu of t is e to the power of the integral from a to t of p of u du. And this p of u right here is this function that's multiplied by y right here. Yeah, so it's pretty crazy. Like, how did he come up with that? I don't know. But he discovered that if you have this function here and you multiply by this equation, we're going to be able to solve it. So let's multiply it out. We have y prime times e to the integral from a to t of p of u du plus p of t times e to the integral from a to t of p of u dt times y equals g of t times integral times e to the integral from a to t of p of u dt. P of u du. I'm sorry. This should also be u, and everything now is consistent. Okay, so yeah, we multiply everything out, and then he saw that when you write it this way, we can remember that the product rule is that whenever you have two functions and you take the derivative of these two functions, you keep the first function and you multiply by the derivative of the second, and then you add the derivative of the first multiplied by the second. So this is the product rule that we learned in Calc 1. And he saw that this left side of the equation can be written as a product rule. So see if you can follow with me. If you differentiate y, we're going to have y prime. If we differentiate, and then we're going to keep one of our functions. So we're going to keep e to the integral. So we're going to keep the integrating factor. And then you add, if you differentiate the integrating factor, you see this term p of t is going to come because we're going to have e to the pt. And then when we differentiate this, we're going to have p to the t e to the pt. It's kind of hard to visualize since it's in this form, but like when we solve exercises, it's going to become a lot clearer. I remember the first time I saw this derivation, I thought it was too messy. Like I couldn't understand it very well, but it makes a lot of sense once we go through exercises. So don't worry if this seems a little bit confusing. Next video, I'm gonna solve like many exercises, and I'm pretty sure you're gonna be able to follow up with everything. But let's continue. So this expression here, we can rewrite it as the derivative as y times the integrating factor. I'm just going to write it mu of t. And the left side, we just copy it because we didn't do nothing to it. So instead of writing this, I'm just going to write it as mu of t, the integrating factor. And ultimately what we want is we want y of t, like we want the solution of this ODE. So what we do to get the solution is that we integrate both sides with respect to t. And since integrals and derivatives, they kind of like undo each other, what we're going to be left on the left-hand side is we're going to be left with the argument, because this integral and this derivative are just going to undo each other. So we're going to have, let me erase this part right here. So I'm going to erase this part right here, ODE. Okay, so what we're going to be left with the left side is y times mu of t is equal to the integral g of t mu of t. And when we compute this integral, we're going to come up with a constant. A constant is going to appear. And then ultimately, when we solve, we're going to have the integral g of t times mu of t dt. Sorry, 1 over mu of t plus c over mu of t. So this is the solution of our first order linear ODE, and I don't want you to memorize this. I just wanted to show you like in the most like abstract ways using functions instead of numbers. But as we go through examples, it's going to be crystal clear. So don't worry about it if you didn't understand this part as much. Just watch my next video. We're going to solve many examples. But the thing that I do want you to learn from this, from what we talked about today, like the most important thing about first order linear ODEs is the integrating factor. The integrating factor is how we know how to solve first order ODEs. Like there are other ways as well, but it's actually not that bad. I wrote the integrating factor in a different form, but as we're going to see in examples, I wrote it as p of t instead of p of u, and I didn't write the bounds. But next video I'm going to explain why. So this is just something that I would highly recommend you to memorize. This is the integrating factor, and no limits of integration are needed. Yeah, as we're gonna see, the limits kind of goes away as we're solving the problem. We don't need to write it, and when we solve examples, it's gonna be clear like why they're not needed. Just commit this integrating factor, this expression here, to memory. Thanks a lot for watching this video. Next time we're going to solve examples of linear ODEs, and if this explanation wasn't clear right now, I remember it wasn't for me the first time I learned it, like solving with everything in functions. It wasn't the best way to learn it for me. I particularly learned through the examples shown in class. So please be sure to watch my next video. It's going to clarify a lot of things, a lot of questions that you might have. Alright, I'll see you next time.